Let us now consider the special case of free vibration. In other words, vibration with no external forces, with no damping. In other words, there is no loss of energy, damping or friction. Okay, so recall that this is the situation we are considering. We have a spring attached to a mass, M, spring stiffness K, and we are measuring X from, X is measured from the free length or the stress-free length of the spring, okay? Right, it's also called as free length, force-free length or stress-free length. Etc. Okay, so that's what we're measuring X from. In other words, when you're not, when it's not vibrating, the system will just sit with the mass M at X equal to 0, right? So when it's just sitting still, it'll sit at X equal to 0. But then what we're going to do is pull the spring by pulling on the mass and then let go, and then it will oscillate back and forth like so. And we would like to derive an expression for that motion, okay? So again, just to recall very quickly, the free body diagram looks like this. There is no rightward force. The leftward force is K times X. Okay, and there is a vertical direction forces, mg and n, which just cancel. So the equation of motion is ma in the x direction equals minus kx, or mx double dot equals minus kx, or mx double dot plus kx equal to 0. Okay, so this is sort of the famous equation for free vibration with no damping. When we say free vibration, we mean that there is no external force on it. When we say there is no damping, we mean that, well, there is no damping. A damping is when you have another object in parallel which damps out the vibrations, takes energy away from the vibrations. Okay, so let's just first consider this equation in detail. Okay, let's call this equation number 1. We would like to derive an expression for x of t, okay, that captures, that describes the vibration of mass, the free vibration of mass m. Okay, so what do we do? Well, first of all, we kind of intuitively know that the motion is going to be some kind of an oscillation, okay? And we can sort of use that intuition to try out various potential solutions for this equation, okay? So this is an equation all of you guys have seen in your differential equations class in mathematics, but we're going to do this solution again in this class just so that it really fixes the idea. And this is an equation that you will encounter in your coursework over and over again. So let's look at this equation in greater detail. Okay, so we know that the motion will be an oscillation, and because there's no friction or damping, it's an oscillation which will persist forever. Okay, so based on that, let us try x of t equals, well, oscillations kind of ring a bell, so to speak. So the simplest kinds of oscillatory motion that you can imagine are sines and cosines. So let's say it consists of sine something and cosine something. Okay, now it's not going to be just sine t. Sine t has a particular frequency. We don't know what frequency this object is going to oscillate at. So let's say sine omega t, where omega is some kind of a frequency. Higher the omega, faster the oscillations. So cosine omega t. And we don't know what the amplitude of the oscillation is going to be. So we say A sine omega t and then B cosine omega t, or actually B sine omega t, A cosine omega t, it doesn't matter. Just to be consistent with the book, let's say B sine omega t, A cosine omega t, and I'm going to pull this here. Well, let me just erase it and rewrite it. So let's say A cosine omega t plus B sine omega t, okay? Okay, so this omega is unknown frequency, allows for different frequencies. And A and B allow for different amplitudes, okay? Okay, so let's call that equation number 2. And let's plug in equation 2 and equation 1, okay? So to plug it into equation 1, we need to find x double dot. So let's find quickly x double dot. X dot is going to be minus A sine omega t minus A omega sine omega t plus B omega cosine omega t. And then we differentiate again. The omega comes out of the sine and cosine again. So we have minus A omega square cosine omega t plus B, or minus B omega square sine omega t. So plug in 1. So let's call this equation 3. Plug 3 and 2 in 1. So recall equation 1 is mx double dot plus kx equal to 0. So let's plug in m. X double dot, we just said, was A omega square cosine omega t minus b omega square sine omega t plus k is a cosine omega t plus b sine omega t. This whole thing is equal to 0. Notice we have some things that are very similar. So we can omega square, we can remove the omega square outside. So we have minus m omega square. And then once you remove the omega square, all you have left is a cosine omega t, b sine omega t. So let's write that down. Okay, and then we have a k, a cosine omega t, b sine omega t. The whole thing is equal to 0. And now we can take this outside. So we have minus m omega square plus k times a cosine omega t plus b sine omega t equal to 0. Okay. Now this quantity, this whole quantity should be equal to 0 if this were to be a solution. Now that's only possible if this quantity is equal to 0. Okay, so if this quantity was equal to 0, then it sort of means that x equal to 0 for all time, right? Because that's basically your solution for the motion. So this quantity cannot be 0 unless the object is just literally sitting there and not moving. So that is clearly a solution, but it's not the general solution. So if you want the general solution, this cannot really be equal to 0, but this has to be equal to 0, at least for this assumed form of the solution. Okay, so implies k minus m omega square equal to 0. Okay, because a cosine omega t plus b sine omega t equal to 0 means x of t equals 0, and that's not what we want. Okay, that's what is the so-called trivial solution. And the word trivial solution in mathematics does not necessarily mean that it's too simple to find. It really just means very often that it's the solution that has the quantity equal to 0. Okay, so it really just means 0 solution most of the time. It doesn't mean that it's too easy to find. In any case, so this is the equation that we have when we plug in this expression for x into the differential equation. We plugged it in, we simplified, we are essentially canceling this term, and what we have is this quantity. So what does this quantity tell us? Well, k is a constant, m is a constant, omega is something that we assumed in the form of the solution as some kind of an unknown frequency. So let's solve for omega. Omega square equals k over m, or omega equals square root of k over m. Okay, so omega equals square root of k over m. Omega is often called the angular frequency of oscillation. Okay, units of you can use whatever units. You can say just second power minus 1, which is the same as hertz, or if you want to make clear the angular part of the angular frequency, you can say radians per second, or that's basically it, right? So and recall, radians is not really a unit, so radians per second unit is the same as a per second unit, right? So these are all exactly the same units. So anyway, omega has those units. If so, let's talk about that. What omega means in a second. So let's leave that aside and denote that expression for, okay? That's the angular frequency. This is the definition or the relationship for the angular frequency. Okay, so now what are A and B? What are A and B? How do you find A and B in this expression? You've just found the expression for omega. Omega just depends on the mass m and stiffness k. You can sort of talk about the meaning or the mechanical intuition provided by this expression, square root of k over m. You can see that omega increases with increasing k. Right? In other words, if you increase the stiffness, if you increase the stiffness of this object, it will oscillate with faster frequency. If you lower the stiffness, in other words, you make the spring really soft, the mass will go back and forth more slowly. And then it says that omega decreases with increasing m. So it says if you increase m, omega will decrease. In other words, the frequency will decrease. So for a given spring stiffness, if you increase m, the mass will sort of moves more slowly. Okay, that's what this expression implies, right? So if you, for instance, want to increase the frequency of natural frequency or the angular frequency of the system, you want to increase the stiffness, and if you want to increase the frequency, you want to increase the stiffness and decrease the mass. Okay, so omega is called the natural angular frequency. It's also sometimes called natural frequency. So usually it's denoted, this quantity is denoted by omega n, which is square root of k over m. Okay, n denotes natural frequency of the system. Okay, sounds good. Okay, so we'll talk about omega and how it relates to the exact frequency with which the things oscillate in a minute. Let's next find the value for A and B. Okay, what are the values for A and B? So to find A and B, we need to know what started the oscillations. In other words, we need to know what the initial conditions are. Okay. From knowledge of initial conditions. Right, so A and B has something to do with the amplitude, and of course the amplitude will depend on, well, how much did you pull the mass and let go to start the oscillation, or what initial velocity did you give the mass to start the oscillation. Okay, so we need to find A and B based on the initial conditions, namely the initial positions and the initial velocities. Okay, so say x naught is the initial value of x, and x dot naught is, or sometimes called v naught, is the initial value of x dot, right? So basically equal to x of 0. This is x dot of 0. So let's use those to, we recall x of t is a cosine omega t. plus b sine omega t. Now I'm going to start replacing omega with omega n. Okay. Okay, so because we're going to use the term natural frequency for this, we'll talk about that in a minute. Okay, so that's x of t, and we're going to plug that into these two expressions. So x of 0 equals x naught. So what we have is a cosine 0 plus b sine 0 equals x naught, or sine 0 is 0, cosine 0 is 1. So a equals x naught. Okay, so you just solve for a. Let's call that 5. And then let's solve for b, which we do by substituting x dot at time t equals 0 equals x naught dot. Okay, so we do that by first determining what x dot of t is, and we can just differentiate that. We already did it in the past, but we can do that again. A omega sine omega t plus b omega cosine omega t. And then we plug in t equal to 0. So you get minus a omega times 0 plus b omega times 1. So what we have is this is equal to b omega, and we said that's the whole thing is equal to x naught dot. This equals b omega equals x naught dot, or b equals x naught dot divided by omega. Okay, so that's equation 6. So now we have an expression for a and b. So the full expression, plug everything back into the original expression, plug 4, 5, and 6 in, or at least 5 and 6, so that the expression doesn't get very unwieldy. In equation 2, we get essentially that x of t equals x naught cosine omega t, omega and t, plus x naught by omega sine omega t. Okay, so this is the expression that describes the oscillatory motion of a simple mass spring oscillator. Okay, so this object I might call a mass spring system. It's also called sometimes a simple harmonic oscillator. Okay, and this motion is called simple harmonic motion sometimes. And because it's basically a sum of cosine and a sine, the motion in general looks something like a sine or a cosine shifted. We will do a separate video on that topic. Okay, so but this motion essentially is a motion like this with period equals, the natural period will be equal to 2 pi divided by omega n. So that's something that we shall see in the next video. The main idea, takeaway, is that we've derived an expression for the motion which involves the initial conditions, x naught and x dot naught, and omega n, which itself is a function of the stiffness and the mass. Okay, so that's a big answer. That's a big equation. Okay, so let's call that equation number 7. And this equation is something that you will find. Some version of this equation is something you might find on your formula sheet. But really, you should be able to, given the expression, you should be able to take this expression, plug it in the differential equation, and then solve for omega as well as the unknown constants a and b in terms of the initial conditions. That's something you should be familiar with. But in the context of an exam, we will have this formula on the exam sheet.